Hello, this is Dr. Webb, and in this video we're going to look at a very important strategy called integration by parts. So our goal right now is we want to be able to evaluate integrals where we're multiplying two functions together, where we have two functions multiplied together. So we're looking at integrals of the form f of x times g of x dx. And same as with many things in integration, we're going to sort of, to get a handle on how to do this, we're going to start thinking about, well, how do the derivatives of products work? So from Calc 1, you remember the product rule. If we have u of x times v of x, we take the derivative, well, it breaks into two things. We've got u prime times v of x plus u of x v prime of x. And so, in integration, we're kind of thinking about the inverse process of this, trying to undo this. So to kind of think about what happens, we're going to go from here and think about what happens as we integrate both sides. So let's integrate both sides in terms of x. So on the left-hand side, since we're integrating a derivative, they're going to basically undo each other. And so we'd have u of x v of x back. And then on the other side, we can rewrite this as two separate integrals plus, now we've got the other one. And we notice that on the right, both of these two integrals on the right-hand side have this form of two functions getting multiplied together. So we're going to solve for one of those. I'm going to take this one, solve it by itself. So integral of u of x v prime of x dx. And so this is going to be equal to u of x v of x, and then this other integral is going to be essentially moved to the other side, so we're going to have to subtract it off. Right? And so now you can see on the left-hand side, we're starting off with integrating a product of two functions, and now we have, we have what it's one way to think about what it would be on the right-hand side. So on this left-hand side, we can think about, maybe this u of x as being our f of x, and the v prime of x dx, this being the g of x dx. And so this whole integral is, we're integrating f of x g of x. And sort of the hope at the end is, while we do get the u of x v of x, we do get another integral. Our hope is that this integral is easier to deal with than the original. So we want that extra integral we get at the end to be less of a hassle than what we started off with. And if that's true, then this has worked. Right? And so the idea is we start off with an integral of f of x g of x dx, that one of these we're going to think about as being u of x, and then everything else is going to become v prime of x dx. And so the integral is going to turn into, we're going to rethink about it as being u of x times v prime of x dx. And so then we get this rule that we had on the last slide, that the integral, that we can rewrite this integral as u of x v of x times the integral of v of x u prime of x dx. And again, the goal is this should be nicer than what we started off with. And so there's a shortening of this, a way to write this more quickly. Rather, we're just going to kind of drop the x's. And the u of x we're just going to write as u. And then the v prime of x dx, we're just going to write that whole thing as dv. And so this is the normal formula for integration by parts, is that if you integrate u dv, you get back uv minus v du. So let's try this out. So we're going to integrate. We've got two functions here. We've got x and we've got sine of x, and they're multiplied together. And so for our purposes here, we're going to let u be x. And so that's my u. And so then that means that everything else here is the dv. So dv is going to be sine of x dx. Then to get du, well, this is just going to be the derivative of x. And so the derivative of x is 1, but I'm going to rewrite it as 1 times dx. On the other hand, to get v, well, v really is integrating dv, and so this would be the integral of sine of x dx, and that's an integral we know how to do. That's going to be minus cosine. We can pick for our v. And so then our integration by parts rule, integral of u dv is equal to uv minus v du. We can plug everything in. So u times v would be minus x times cosine of x. And then we'd be subtracting off the integral of, well, v, and so that's minus cosine. And then times du, but du is just dx. Right? And so we've got two minuses here, so we can cancel this off. And so this turns into x minus cosine x plus the integral of cosine x dx. And if you notice, at the end we have just the integral of cosine, and this is an integral that we can do immediately. And so to finish this off, this means that the integration by parts has worked. And the integral of cosine, that is just sine. And we need to put a plus c at the end. Right? And so now we have found an antiderivative. Okay, so this is how it works. And so the idea is we start off with a nasty integral. We apply this integration by parts. We get another integral, but the integral we get at the end is nicer than what we started off with. Okay, and so you might say, does it matter how we choose these? So we'll go back and look at the same integral again, but what happens if we flip? So originally we picked x to be our u. What if we picked sine of x to be our u? And then that means that everything else that we are left with is going to be our dv. And so dv, if we take sine x to be u, then everything that's left is x dx. Du, well, that's going to be taking the derivative of sine, so that's going to be cosine x dx. And our v, well, so that's going to be integrating x dx, and the integral of x is, antiderivative of x is x squared over 2. Okay. And so now if we apply the integration by parts rule now, so u dv is equal to uv minus the integral of v du. And so we would get u times v would be x squared over 2 sine of x minus, well, what's the integral we get? So v x squared over 2 times du, cosine of x dx. And now looking at this integral we got at the end here, this is not nicer than we had before. So this has gotten worse. And so this means that this was not a good choice for u in dv for this integral. So how you pick your u and how you pick your dv are very important in terms of doing integration by parts. If you pick them poorly, you will end up with something worse than what you started with. Right? So how do you choose what should be u and what should be dv? And so the mnemonic device for this is there's two forms of it, either liate, L-I-A-T-E, or ilate. And so these letters stand for, well, the L stands for logarithms, I stands for inverse trig, A stands for algebraic functions. So algebraic functions, this would be something like polynomials, rational functions, roots, trig functions, or exponential functions. And so the idea here of the liate is or ilate is that the ones that are higher up, the higher up ones, these are going to be your u's. The lower down ones, the ones that are lower down on here, or the ones that are later in the word, this is how you're going to pick your dv. Right? So in the original example, we had x times sine of x dx. So we're looking at the x and the sine of x. The x, that's algebraic. And the sine of x, that's a trig function. And so looking at here, a is coming before t. And so that means that we want x, our algebraic function, that's going to be our u. And sine of x, our t, our trig function, that's going to be our dv. And if you go back, this is our choice of u and dv that worked out nicely. Right? And so the idea here is that for the ones earlier on, the L's, the I's, and even the A's, that they are generally functions that are harder to take integrals of, and that when you take derivatives of them, they become something easier. Right? So if you take a derivative of a logarithm, like natural log, you get 1 over x. Well, that's now algebraic. Same thing if you take the derivative of something like arc sine. Well, the derivative of arc sine is 1 over square root of 1 minus x squared. So that is also an algebraic function because it's a root in a fraction. So by taking, those are become u's because on the other side, in the new integral, they will become the du's, and so they will be simpler than what they were before. On the other hand, for the trig functions and the exponential functions, the ones at the end, they're functions such that when you integrate them, they generally don't get worse than what they were before, right? So the integral of e to the x is just e to the x. It stayed the same way. The integral of sine turns into cosine. Cosine's no more difficult than sine. And so this is where the idea is coming from, that by following this rule, your new integral at the end, your integral of v du, should be simpler than what it was that you started off with. All right, so let's close with one more example. We're going to integrate just natural log of x dx. And so you might say, well, this doesn't really look like a product because we just have natural log of x there. But if you think about it, we don't know how to do this right off the bat. You can't think right off the top of your head what's a function whose derivative is natural log of x. It's just natural log of x. But we can still use this idea of integration by parts. And so ln of x, that's a logarithm, so that's going to be our u. And then for the dv, Well, dv is just going to be everything that's left. Well, if u is ln of x, what's left? Just dx. Right? So natural log is going to be our u, and dx is going to be our dv. And so now we can get du, derivative of natural log of x, is just 1 over x dx. And then v is going to be just, well, what's the integral of dx? Antiderivative of dx is just x. Antiderivative of 1 is x. And so we can use that. And so now, applying integration by parts, u dv becomes uv minus the integral of v du. So u times v, I get x times natural log of x. And then now v, 1 really is an algebraic function, and so it turned into x, which isn't really that much worse than it was before. And then now our du, our logarithm now has turned into something easier, 1 over x dx. And so looking in here, we have x times 1 over x. And so this becomes x natural log of x minus, well, they cancel themselves off. And so we just have the integral of dx. And so we have x natural log of x. That becomes x, and then we should include our plus c at the end. That is all for this video. Thank you for watching, and I will see you again soon.